Hi everyone, I'm Professor Bergasser. In this video we're going to be looking at how we can solve for rotational and translational motion problems using rotational energy. And as a reminder, an object that's spinning, that spinning motion contains a kinetic energy component. That's rotational kinetic energy. And through various applied torques, that kinetic energy can change, but really what happens is it's being transformed between different forms. So you can see kinetic energy being stored as rotational potential energy, or it can be dissipated into energy lost to the system, or it can be transformed between rotational and translational kinetic energies as well. So we're going to be looking at a much broader system of energy as we look at both translation and rotational motion. And just keep in mind our definitions. The definition for kinetic rotational energy looks very similar to that of kinetic energy for translation. It's just that we've replaced our mass with our center of mass and our velocity with the angular rate squared. And then the change in that is just equal to the rotational work, which in this case is equal to the applied torque over the angle or angular displacement at which that torque is applied. And again, these are directional quantities, and so it will depend on whether the torque is applied along the rotational motion or against the rotational motion. You'll either have more or less kinetic energy. You can also compute the potential energy from rotation using our work energy theorem applied for rotation. And of course the change in the rotational energy, kinetic plus potential, is just going to equal to the torques that arise from dissipative forces. And because there's a possible exchange between rotation and translation, what you really want to do is calculate the work done in translational motion, force over displacement, and the work done by dissipative forces that corresponds to the torque, which is the torque over the rotation angle. So we're going to follow a process that's very similar to the process we followed for looking at solving translational motion problems. And that's, of course, computing our initial and final kinetic and potential energies. But we're going to do this for both translational motion and rotational motion. Keeping in mind that rotational motion will be computed generally about the center of mass, although we'll see an example where we can compute it about a different point. We're going to compute any rotational and translational work done by dissipative forces, because those are the things that can change the total energy of the system. And then we're going to look at the change of the total energy of the system being a combination of all of the kinetic energy, translation and rotation, all the potential energy, translation and rotation. The change of that large amount of energy is just equal to the sum of the dissipative work done by dissipative forces, both in translation and in rotation. We'll see an example of that a little bit later. Then, of course, if there's any constraints to the motion, we'll want to apply those, solve for our unknowns, and of course the most important step is checking our answer at the end of all of our solution. So as a first example, let's revisit one of the problems we've done before, and that's looking at a ball that's rolling down an inclined plane. In this case, let's assume it's a solid ball, so it has a moment inertia of 2/5 mr squared, about its center of mass. And as before, we can ask, what is the speed of the ball as it reaches the end of the platform and rolls off to the side? What is that speed, assuming that it rolls without slipping? And that's an important phrase, rolls without slipping, because what that implies is that we have no dissipative forces acting. Friction is acting in this problem, but it's acting to transform translational motion into rotational motion. You don't have two surfaces sliding relative to each other, so you don't have any loss of energy from the system. So this is an energy conservation problem, so we can very easily just write down the initial and final energies, both rotation and translation, to figure out what the final speed of the ball is. Okay, so let's go ahead and write these down. We're now going to have three categories here. Kinetic energy of rotation, kinetic energy of translation, and any potential energy in the problem. And generally, it's very rare that we'll have a potential energy of rotation that might be a torsional spring or something that winds up as you're winding around. In this case, we just have a regular ball. There's no forces that are acting to twist this up in some way, and so we'll mostly just be looking at potential energy from translation. All right, so if we look at our initial state, we've got a kinetic energy of rotation, which is 1/2 times I times omega squared. And actually, let's take a step back because I'm starting this problem from rest. So it says we're releasing from rest. That means there's no speed of translation. There's also no speed of rotation. So I don't actually have to write anything down because it's 0 for both of these for our initial kinetic energies, starting from rest. However, there is an initial potential energy in this problem because I've set this ball up a height h above this, up on this inclined plane. And we know from potential energy that that's just equal to mg times h for a potential energy term. So that's all of the initial energy for our problem. The final energy of our problem is going to be a combination of our rotational rate, rotational speed, so I'll call that 1/2 I omega squared, our translational speed, 1/2 mv squared. I'm actually going to make these primes so they indicate that they're after the motion has completed. And then the potential energy, in this case we're just looking at gravity as our source of our conservative force that gives us a potential energy. And if we set the 0 point for our problem here, where we get to 0 at the bottom of the inclined plane, this potential energy is equal to 0 as well. Now, so these lines give us the total energy of the system, all right, kinetic plus potential. And this is the case where it's important to note that because we're rolling without slipping, that means that our initial energy is equal to our final energy. And so we can very quickly write down that this means that mgh is equal to 1/2 times I omega prime squared plus 1/2 m times v prime squared, our final quantities. Okay, so that gives us a starting basis for solving for this equation, but notice that we have two unknowns, the final rotation rate and the final speed of the object as it rolls off, and just one equation, so we're going to need another constraint on this problem. Well, the constraint comes from this, again, the same phrasing, it rolls without slipping. And that means that as it's rolling, it is covering just as much space along the surface of the ball as it covers horizontally on the surface of the table. So we've seen this constraint before. This constraint gives us that r times the rotation rate is equal to the translational velocity, and this is true for any point along the motion, as long as it's rolling without slipping. You need that so that it doesn't actually have the two surfaces sliding relative to each other. All right, so that gives us our enough quantities, and so if I substitute back in, let's actually substitute back in the velocity here. So we'll put that in for r omega. So I'm going to have mgh, and let me explicitly write down the moment of inertia here. So that's 1/2 times 2/5 times mr squared times omega prime squared plus 1/2 times the mass times r squared omega prime squared. Okay, so combining that, that's 1/5 and 1/2, so that turns out to be 7/10 mr squared omega prime squared. And you can see we can cancel out our masses, and we can get a final expression for our rotation rate, omega prime, is just equal to the square root of 10/7 times g times h over r squared. Okay, so that is our final rotation rate, and notice that it depends on the height and inversely proportional to r squared. And we can check our units. The units of these of g is meters per second squared times meters for our height divided by meters squared. Those cancel out, and we get a 1/second squared, and the square root of that is 1/second, and that is the units of rotation rate. It's radians per second, radians being a unitless number. All right, so that gives us the right value for that, and because of our constraint equation, we can immediately write down our final speed as just r times omega prime, and if we carry the r through there, that's just equal to square root of 10/7 times gh. And again, we're going to have meters per second squared times meter. That's meter squared per second squared, square root meters per second. That's a velocity. All right, so that's our solution. And notice that this was much faster to get to than the original problem because we're just looking at initial and final states rather than computing out the equation of motion throughout the entire process. So as a second example, let's take a look at the motion of a bar that's released from rest on a pivot. This is going to give us an example of how we can look at different ways of measuring the rotational kinetic energy depending on the perspective at which we want to choose. And we're going to look at how that translates between different rotational and translation energies. So here's our setup. We have just a regular bar of length L that's going to swing down. And we want to find out what the motion, the speed of the bar is as it passes through the bottom part of its motion. Now we've seen exactly the same kind of problem with regular simple pendulas, and of course we saw that energy was a very easy way to calculate the speed at any point along this motion. So let's see how this applies for the case where we have to take into account the actual rotational momentum or rotational motion, rotational energy of the spinning bar itself. Now, as I mentioned, there's two ways that we can look at this motion. Either the translation of this bar and its rotation about the center of mass, which is the approach we've taken so far, or we can look at it as just a rotation of this bar about the pivot point. Now, we should get the same answer in both cases because it's the same motion, but let's see how we actually compute that. So the first case I'm going to look at is the rotation about the center of mass. And as before, we're going to write down expressions for the rotational kinetic energy, the translational kinetic energy, and the potential energy in the initial and final states. And as before on the last problem, the bar is released from rest, so the kinetic energies, both translation and rotation, are equal to 0. And the potential energy is just how much the bar starts above its final mass point. And it's important to remember this is the center of mass point because that's where gravity actually acts. And so you can see that it's going to rotate down. It's going to be halfway down from the pivot point is where the center of mass is. So the potential energy is just its weight times L over 2. All right. In the final state, we're going to have some kinetic energy from the velocity, some rotational kinetic energy, 1/2 I omega squared. And assuming that we've chosen that to be the 0 point, this is just going to be 0 potential energy at the end. Now, as long as I don't have any dissipated forces in this problem, which might be dissipation or friction in the pivot wheel, if we can ignore that, then the total energy is conserved from the initial to final state. So we can simply write down EI is equal to E final, and that gives us an equation, but two unknowns, the velocity and the rotation rate. So how do we disentangle those? We need a constraint equation. Now, what's the constraint equation? Well, let's think about this motion a little bit. We've broken it down into the motion of center of mass and the rotation about the center of mass. And at this bottom point, you can imagine that the motion of the center of mass is pointed off in that direction. So we'll call that V. And at the same time, it's rotating about that center of mass with an angular rate of omega. Now, this bar is pivoted at one fixed point along the end. And for that to be the case, we have to cancel the velocity of motion going off in that direction and the effective velocity, the angular velocity, that's coming as omega times this length arm. So for those two to cancel out, the amplitudes of those, the speed, is going to have to equal the rotation rate times L over 2. This is the constraint of our pivot point, all right, our fixed point. And of course, it looks a lot like the constraint we've had for rolling objects because, again, at those points you have to have no relative surface motion. This is kind of the same argument that there's no motion at the pivot point. Great, so that gives us two constraints, two equations for two constraints, for two unknowns. And so we can go ahead and write down our energy conservation, mgl over 2, is equal to 1/2 mv squared plus 1/2, and I'm going to explicitly put in the moment of inertia of the bar about its center of mass. That's 1/12 times m times L squared times omega squared, but omega is just V times 2 over L. So V 2 over L quantity squared. And we can cancel out the masses in this case. And notice that we will bring out at 1 over L squared from here, which will cancel out this L squared. And then we're left with a 4 divided by 24, which is a 6. And when you combine all these numbers together, a half plus a 6 gives us 2/3 times mv squared. And actually, we've already canceled our m, so it's just 2/3 v squared. Write that a little bit better. And so if we isolate our quantity of velocity, multiply by 3/2 on both sides and take the square root. This is going to be 3/4 times g times L as our final speed. All right, now we should always make sure we check our answer that it satisfies the units. G has units of meters per second squared. Length has units of meters, so that's meters squared per second squared. Square root gives us a speed of meters per second. So at least unit-wise, we know we have the right value. All right, now that's calculating this relative to rotation about the center of motion. Let's try another case where we look at rotation about the pivot. Okay, so again, we're going to look at the kinetic energy of rotation, the kinetic energy of translation, and the total potential energy, initial and final. Potential energies don't change in this case. Too many L's in my final. Potential energy doesn't change in this case. We still start with mg/L/2 of potential energy in the gravitational field and end up with 0 at the bottom. What does change is when we calculate the kinetic energy of the rotation. In this case, of course, we're starting with 0 for both of these. But at the bottom of this, we're really looking at rotation about the pivot point alone. And so that gives us a 1/2 times I of the pivot. And just to make sure I'm clear, I realize I didn't put these the opposite way. So this is translation and this is rotation, just to make sure that's clear. All right, so this is the moment of inertia about the pivot point times the rotation rate, omega squared. And because that pivot point is not moving, in fact, we've got no translational energy of that point on our bar. All right, so how do we deal with that? Well, let's take a look at this more clearly. Remember that the pivot point moment of inertia is going to be the center of mass moment of inertia plus the offset I have to go from the center of mass to the pivot, which is just L/2. So this is equal to 1/12 times ml squared, which is the center of mass moment of inertia, plus m times L/2 quantity squared. And when you do the math for that, that gives us 1/3 ml squared. And it should be very clear now that I've actually put more energy into rotation here because this number is a bigger number than the 1/12 ml squared I used before. So I've kind of hidden some of my translational motion into rotational motion by choosing the pivot point as the point at which I'm going to measure these quantities. Well, let's see how that does. So again, we've got actually just one equation now, and in fact, we've only got one unknown, so we don't even need our constraint equation because I've chosen the pivot point to be a point at rest. So I can immediately write down that 1/2 times 1/3 ml squared omega squared is equal to mgl/2. Our masses cancel. In fact, so do our 1/2s and one of our L's. And we derive that the rotation rate of the object is going to be equal to the square root of g, so let's make sure we get numbers here, 3g over L. Now that's a slightly different quantity than we had for our velocity, and of course it's a different physical quantity, so it's going to have different units. But now let's calculate what the velocity is based on that rotation rate, and remember it's rotation rate about the pivot point. So we're interested in the mass at this point at the center of mass. Well, that's just the rotation rate times the length of arm at which we're rotating on, the radius of that rotation. Well, that means the velocity is just omega times L/2. Notice that our constraint equation comes back in again. Well, if we sneak in our L into the square root, that gives us L squared over L, so that's L over top, and then the 2 becomes a 4. So this is 3/4 GL, and we get exactly the same expression that we got for our other format. So in this case, either one of these solutions would have been fine. Notice that this is actually an easier way of calculating, for example, the speed at any point along this bar. So if, for example, we want to calculate the speed at that point on the bar, it's just multiplying omega times L as opposed to L/2. So both processes give the same solution, and it's just important to make sure you're consistent with the way that you're calculating these numbers depending on which perspective you take. Now the last two problems assumed energy conservation because we have no dissipative forces acting. It's worth looking at an example where we do have a dissipative force, say a friction, acting in a problem, and how that affects the energy change in the system. So we're going to go back to one of our previous problems where we looked at a cue ball that's been struck with a cue stick. It initially slides across the table, but eventually will start to roll, and at some point later on in the motion, it will roll without slipping. Now, we actually computed the last time what the speed of the ball and the rotation rate of the ball is after this interaction. We did it using just our regular kinematic relations. Now let's see if we can apply an energy approach to get some insight into this problem from the energy perspective. So as before, we're going to look at the kinetic energy of rotation, the kinetic energy of translation, and any potential energy in the problem in the initial and final states. In this case, we're starting the ball off with zero rotation. We're just smacking it right in the middle, so we're just giving it a translational motion, which is 1/2 mvi squared. And because we're keeping the ball at the same height throughout the process, and because friction is not a conservative force, a dissipative force, we don't actually have any potential energy either initially or finally in this problem. So we're not going to consider potential energy at all in this case. Now for the final motion, of course, we're going to have 1/2 I omega final squared and 1/2 mv final squared. And then we also have the constraint, because at the end it's rolling without slipping, that the final speed is equal to r times the rotation rate, where again r is the radius of the ball. All right, now let's look at our equations. We've got two unknowns, omega f and vf, and we've got this constraint equation. So if this was energy conservation, we'd be done. However, it's not. Because there's a dissipative force, we cannot assume that the initial energy and the final energy are the same. In fact, we should assume that some of the energy of the mechanical energy of the system is lost to things like friction and sound and vibration. So we have to actually go and calculate explicitly what the work done by those dissipative forces actually is. So in order to do that, it's important to draw a force diagram to get an idea of what forces we're talking about. Just as we've seen before for any kind of rolling ball, and we saw in the problem before, we're going to have a weight term acting down at the center of mass. We've got our friction force that's going to be pushing in the opposite direction at which the ball is sliding. Of course, remember this both slows down the translational motion of the ball and rolls it up. And we also, of course, have our normal force of contact between the surface of the table and where the ball rests. So knowing those forces, we can go ahead and calculate what the work done by the frictional force is, both in translation and rotation. So for the translational work, this is just equal to the minus the force of friction times the displacement over which that friction force acts. And we could actually explicitly calculate what that friction force is, but we'll see in a moment we don't really need to worry about that too much. We can also then calculate the work due to rotation. And now this takes a little bit of thought. If we think about how the ball actually operates, it starts with zero rotation, and then it spins up. All right, it goes from zero kinetic energy, we actually wrote down here, zero kinetic energy of rotation, and then it has a non-zero positive kinetic energy of rotation. So the work done on the ball by the friction force has to be positive work. It's adding work. Even though it's a dissipative force, it's actually adding work to the ball. As we'll see in a moment, that's actually not, friction is not generating energy, it's just transferring some of the energy from translation over into rotation. We'll see that in a moment. So to compute that, it's just the torque times the angle of which the object is acting. And if we choose to measure our motion at a point that's maybe parallel to the center of mass, then we can calculate the torque as just r cross f, points into the board. Whatever we want to find it, we know that that's going to add positive work to our motion. So that's going to be the radius of the ball times the friction force, and then times the angle over which this motion is actually taking place. All right, so let's calculate then the change in energy, which is just the final energy minus the initial energy. All right, for the final energy, if we make our substitution that the final speed is equal to r times the the final rotation rate, or in fact what we're going to do is substitute the rotation rate in there. Well, let's write everything down just to make sure we don't lose it. We've got 1/2 times 2/5 mr squared, right? That's our center mass moment of inertia for a sphere, times omega f squared, but that's just Vf over r, quantity squared, plus 1/2 m Vf squared, and then minus our initial velocity, our initial kinetic energy. And again, if this was energy conservation, that would be equal to 0, but in fact we have to set this equal to the work done by the frictional force, both in a translational sense and a rotational sense. And if I just combine those terms, this is the friction force times the combination of r delta theta minus delta x. Now, when we've talked about, for example, when we had the ball rolling down the inclined plane, this expression here, r delta theta minus delta x, was equal to 0 because we assumed it was rolling without slipping. The translation was exactly matched by the sort of surface of the ball that was coming across as it rolls around. In this case, we can't assume that, and in fact it should be clear that the ball as it's sliding is going to have a larger horizontal displacement compared to how much of the surface of the ball is rotating down onto the table. So this is not equal to 0. In fact, it is probably less than 0 because some energy is being dissipated away. And at this point we're actually a little bit stuck from the energy perspective because we don't have an easy way of calculating the relationship between the rotational angle and the displacement angle. One of the great things about having these different axes being independent of each other is we can solve those equations separately. But in this case it kind of hurts us because we can't easily write down a relation between these two. Now, we did solve this problem before, and we solved it by calculating the change in angle and change in position as a function of time using our constant acceleration kinematic relations. And we can go ahead and do that again to solve for these relations. Basically what we need to do is figure out the time scale over which the motion goes from sliding to sliding with, rolling without slipping. We've already solved that problem, so let's not redo it again. Let's just recall that at the end of that, what we computed was that the final velocity, or final speed, is equal to the initial speed times 5/7. Now, it seems like a little bit cheat to go back to the kinematic equations, but we can go back and now figure out how does that translate into change in energy. Well, combining these terms, our delta E, all right, we've got 1/5 here and 1/2, so that's going to give us 7/10 times m times Vf squared, which is in fact, we'll change that to 5/7 Vi quantity squared, all right, to get rid of that term, minus 1/2 m Vi squared. Well, if you go through the math, this is going to be 25 over 49 times 7/10. When you do all the numbers together, what you find is that this is equal to minus 1/7 times m times Vi squared as the change in energy. Or, in terms of the initial energy, which we have here, which is entirely just kinetic energy of the ball, this is about minus 2/7 times our initial energy. All right. So we couldn't compute the energy loss directly through the work terms, but we can compute it by going back to our kinematic relations. And of course we could have solved that as well by going back and solving for these delta thetas and delta x's too. Now let's actually reflect on this a little bit. So it's lost minus 2/7 of the initial energy to the friction force, the dissipative force that's acting between the ball and the table. What if it was just the sliding friction that we're losing entirely? What if it's just a sliding block going across? How much energy would we lose over this same rotation or same difference in speed? Well, in that case, if it was just the work due to translation, right, that work is just the difference between our initial and final speeds. So that's 1/2 m times Vf squared minus Vi squared, which, because we have Vf is equal to 5/7, So that's going to be 25/49 minus 49/49. And if we compute all the numbers together, let me make sure I erase this so I get the numbers right here. This is minus 12/49 times mvi squared. Or if we divide by 2 here, this is minus 24/49 times our initial energy. Now, despite that being a large number, notice that 24/49 is a larger number than 2/7, which is the same as 14/49. This is more energy loss than we actually measured as a result of this motion. Where did the energy go? It didn't get lost. What it went into is changing the translation into rotation. So the rolling motion of this object, that friction force is actually transducing some of that kinetic energy in translation into friction, into heat, so dissipating it, and some of it's going into the rotation motion of the object. So we could easily calculate the different shares of the energy that go in different places, but you can see that that friction doesn't necessarily get rid of all the energy. Sometimes it just moves it from one place to another one. So we've seen some examples of applying rotational and translational motion to a problem. And as we've seen before with just translational energy, some problems really serve themselves to being solved from an energy perspective much more easily than being solved from a, say, kinematics perspective. But there are also cases where kinematics may actually be easier, for example, in shooting a cue ball and looking at the motion of the cue ball after it's slid across the table. So it's important to build up this ecosystem of processes and procedures for solving these problems, because one procedure may work for some problem and one may work for a different one. But keep in mind the process to go about that solution, and as long as you follow the steps carefully, you can very quickly discern what is the optimal way of solving a problem based on the types of techniques that we've studied here.